Okay, in today's video, I am going to go over how to calculate the charges, the capacitances, and the voltage for a combination circuit that contains two capacitors in series, and those two capacitors that are in series are in parallel with a third capacitor. This is the circuit that we are going to use for this problem. You can see we have a 9-volt voltage supply, power supply. We have a 3 microfarad capacitor, a 4 microfarad capacitor. These two capacitors are in series and they are in parallel with this third capacitor, which is a 5 microfarad capacitor. I am going to go over, as I said, how to calculate the total voltage gain in the circuit. No calculation involved. How to determine the equivalent or the total capacitance of the circuit. How to determine the total charge stored in the circuit. And those are my three things: the total, and the total. And then charge, voltage, and capacitance. Then for each of the individual capacitors, we will figure out the charge stored on each capacitor and the potential difference, the voltage drop, gain across each capacitor. Okay, we are going to do all of this hopefully in less than 10 minutes. And I know there is more than one way to skin this cat, more than one way to solve this problem. But I'm going to go through everything step by step, write everything down, and show you how to do all that stuff for this circuit. First of all, very easy, the voltage gain. There is only one voltage supply, 9 volts, so obviously the total voltage in that circuit comes from this 9-volt voltage supply. It is 9 volts. Next, the total capacitance. Okay, we have to basically reduce all of these capacitors down to a single capacitor. All right, and we need to know what is the total capacitance. We're going to use a work on these two first. Okay, we need to simplify this circuit. We're going to do the two capacitors that are in series and figure out the total for those two, which we are going to call C12. Now they are in series. We have to use our 1 over equation. That means that 1 over the capacitance of C1 and C2, C12, is equal to 1 over C1 plus 1 over the capacitance of capacitor number 2. That means it's 1 over 3 microfarads plus 1 over 4 microfarads. Now, to do that on my calculator, I'm just going to do 1 divided by 3 plus 1 divided by 4. They're both 4 microfarads, or excuse me, they're both microfarads. And if I do that, I will get that 1 over the capacitance of number 1 and number 2 is equal to 0.583. All right, this is not the total capacitance of these two. This is 1 over. Remember, when they're in series, you have to use the 1 over equation. All right, so 1 over the total capacitance of 1 and 2 is equal to 0.058, okay, or 0.583. Now, in order to solve for C12, I'm going to take the reciprocal of this fraction and the reciprocal of this fraction, because this is really this number over 1, and if I do that, I get that C12 is equal to 1 divided by 0.583. And if I do on my calculator 1 divided by 0.583, I get that the total capacitance of number 1 and number 2 is equal to 1.75 microfarads. That is the total capacitance of these two capacitors. Okay, C12 is equal to 1.71 microfarads. Now I have reduced these two to a single capacitor, 171, and now I can just add the two together, because now I have one in series with this one, the third one, the 5 microfarad, and you know when we have capacitors, in parallel, when we have capacitors in parallel, we simply add up the capacitances. Okay, so C123, which is basically the total capacitance, is equal to C12, which we calculated and figured out was 1.71, plus C3, which the capacitance of C3 is 5 microfarads. So now they're in parallel and I just add them up. When they were in series, I have to use the 1 over equation. When they're in parallel, I just add them up. So I've replaced these two with a 1.71. So that's 1.71 plus the capacitance of number 3, which is 5. And I get that the total capacitance for this circuit is 6.71 microfarads. Okay, that was a two-step process. First, we had to figure out the capacitance of these two capacitors in series, and then we could simply add up that total capacitance and this capacitance to get 6.71 microfarads. All right? Now we can figure out the total voltage stored in the circuit. Okay, in order to do that, we're going to use Q equals C times V, and we're going to figure out the total charge. So we have to use the total capacitance and the total voltage. The total capacitance we figured out down here is 6.71 microfarads. There's only one voltage supply, so that's 9 volts. So 6.71 times 9 is 60.39 microcoulombs, coulombs being the unit for charge. So now we can see that the total amount of charge that would be stored in this circuit is 6.39 microcoulombs. Okay? So those are our totals: total voltage, total capacitance, and total charge. All right, now we can go on and work on the individual capacitors. What is the charge stored on each capacitor? Okay, the charge that is stored on each capacitor, we're going to just use Q equals C times V, Q being the charge. All right, the charge on capacitor number 1 and the charge on capacitor number 2 are the same. Remember the rules for capacitors. When you have capacitors in series, the charge on each of the capacitors in series is equal to each other. They're all equal to each other. Okay, so we have two capacitors in series. That means Q1 and Q2 are going to have the same charge on them. And how do we figure that out? Well, in order to figure that out, we're going to take the capacitance of 1 and 2. Okay, this is basically Q12. That means we have to have capacitance 1, 2. Now we figured out on the previous slide that the equivalent capacitance of 1 and 2 was 1.71. Well, the voltage drop across these two capacitors that are in series, they're in parallel with the battery. So the voltage drop all the way across from here to here, not the individual voltage drops across each one, we're going to do that, but the total voltage drop across 1 and 2 is 9 volts. Okay, so we're going to figure out the total charge, we're going to figure out the charge across 1 and 2, or charge on 1 and 2. That means we use the capacitance of 1 and 2, and we use the voltage on 1 and 2, and we get that 1.71 microfarads times 9 volts is equal to 15.39 microcoulombs. All right, that means that 60 of the 60, 15 of it is on these two. All right. Now, we could simply subtract 15.39 from 60, and we would get 45. So that's the remaining charge that's on this one, but let's just calculate it and see. So now we want to get the charge on number 3. Now we have to use the capacitance of number 3 and the voltage on 3. Well, we know the capacitance is 5, and again, this capacitor is parallel to this battery. That means there's nothing using any of the energy, so therefore we know that the voltage drop, the potential difference across this capacitor, is also going to be 9 volts. So we have Q is the Q is equal to the capacitance, which is 5, times the voltage, which is 9, and you get 45 microcoulombs. Okay, that's good, because 45 plus 15.39 is equal to 60.39, and that is the total amount of charge. 15 of it is on these two, and 45 of it is on capacitor number 3. All right, so we got those to match up, so that makes us feel that we did that problem correctly, and we probably got the right answer. So now we know the charge that is stored on each of the capacitors. Now we can go and we can figure out the potential difference for each capacitor. Okay, now we're going to use our capacitor equation again, Q equals C times V, but we said earlier that the voltage on 3, because this is a single capacitor, it's in parallel with the battery, therefore we know the voltage across, or the potential difference across capacitor number 3 is 9 volts. Okay, that one's pretty easy. Now we have to figure out the voltages on number 1 and number 2 separately. So the voltage on number 1 is the charge on number 1. Well, the charge on number 1 is the same as the charge earlier that we calculated, the charge on both of them. So charge 1 and charge 2 are the same. The charge on 1 is 15.39, and we know the capacitance, so it's 15.39 microcoulombs divided by 3, which is the capacitance of number 1, and we get 5.13 volts. Okay, now once again, we know the drop, the potential difference across both of them is 9, so we could just take 9 divided by 5.13 and we would get the answer for the voltage on number 2, but I think we'll calculate it also and see if it adds up to 9. So the voltage on number 9 is the charge, the voltage across number 2 is the charge on number 2, which again is 15.39, divided by its capacitance, which is 4, so that's 15.39 divided by 4, and you get that is 3.85. Now if we add these two up, 5 and 3 is 8, this is about close to 1, this is 9.98, so that's pretty close to 1, we'll take that, and that comes right up to just about 9, so that lets us know, or makes us feel pretty good, that we calculated these voltages correctly. Alright, so the charge on these two that are in series, the charge is the same, but they have different capacitances. Therefore, the voltage drops are different. Okay, the voltage drop, the potential difference across number 1 is 5.13, while the voltage drop, the potential difference across number 2, the 4 microfarad capacitor, is 3.85 volts. Okay, you add them up, you get 9. Okay, so I think that's it. We did everything. That seemed to go pretty well. All our numbers seem to match up where we checked things. We did the total voltage, easy. The total capacitance, 2 steps. The total charge, that was relatively easy. Then we did the charge on each of the capacitors and the voltage difference across each capacitor. And I think it all worked out pretty well. So, thank you very much for watching. I hope you found that video helpful. I know that's a lot to do to try to keep it in 10 minutes. If you found that video helpful, you can give me a nice thumbs up in the thumbs up section there, or a nice comment in the comment section below. Thank you very much for watching. We will see you in the next video.